quantum on this one. All right, I got it on this one. That's good. So the title is on different types of mathematical induction. And as I said, the most important thing is that we get an idea what's going on there, that we feel comfortable with the idea. How much we progress with the technology doesn't matter. And I will try very seriously to make it so that it doesn't last beyond 5 o'clock, maybe even 5 before 5, because that's the worst thing you can do about talk, to make it longer than people plan. So you are taking their time. So basically, the main idea for induction is actually here. So can you tell me what do you see there? Can you predict something? Anything, any comments? Completely free, has nothing to do with math.
Dominoes falling.
Yes.
They're all gonna eventually.
Oh, very nice. How many of them are falling?
All of them.
I don't see all of them. I'm sorry. I just see 2 of them. Even they are not fully down. I see number 1 is, it's hard to argue that it will not fall. And I see number 2, the others are standing completely there. Do you agree? But do we all strongly believe that number 3 will start falling in no time? Yes or no?
Yes.
What about number 4?
Yes.
What about number 11?
Yes, eventually.
Okay, so do we all agree that eventually all of them will fall down?
Yeah.
No.
You know, and of course, one can make a model where, I don't know, there's no gravity. This is frozen in, in some of those movies and all that. But in general circumstances, we would agree that they will all fall down. Agree? And if someone challenges that, how would you argue? How would you argue that the number 11 will fall down? Why do you believe that 11 will fall down?
Because each one causes the subsequent one to fall down. So as long as you have the first one, you should have all of them.
So basically, first one will actually is already causing second one to fall. Why? Why is it causing that? Because they are close to one another. Do you agree? Because if I space them widely, they might not hit each other. But the way we space them, then since one is falling, it will hit 2. Do you agree? And then 2 will hit 3, and then 3 will hit 4. And instead of going one by one, can we generalize our argument? And if we generalize our argument, that's called the principle of mathematical induction. And I will write it here. So this is principle of mathematical induction. And then principle of mathematical induction. And I will even formulate that very important theorem about numbers in terms of our dominoes. And that's basically what? If the first one is falling, and each domino will cause the next one to fall. Conclusion, they will all fall down. Does this summarize our argument? Yes or no? So that's how we say, I don't have to say that 3 will hit 4. Or I don't need to say 7 will hit 8. I will say whenever one falls down, the next one will fall. And then basically they will all fall down. Sometimes people like to report this as a machine. And that machine does the following, like a k to k plus 1 machine, that basically whenever someone falls down, it kicks down the next one. So it put one, and one makes two on output to fall down. But now you use that two on input, and that two on input will cause three. And then you keep feeding back, and they keep hitting, and they will all fall down. So basically, this is the principle that we use very often to prove mathematical statements. And how do we prove it? And we call it method of mathematical induction. So we use method of mathematical induction when a variable n taking values among positive integers. So let phi of n be a statement about natural numbers or positive integers. Natural numbers. We get this about natural numbers. Then what do? Number one, we prove phi of 1. Why is that crucial? Because if I don't kick the first one, they will stand there forever, really, however close they are. So you always need to see that that first one will ignite the process. Number two, we assume phi of k for k greater than 1. What do I mean we assume? We think, we say, all right, assume that I already proved that one, or let me assume that fifth one is already falling. So that's what you assume is you conquered that level. And then you need to prove, and that's the crucial thing, prove that, or I don't need that, prove phi of k plus 1. So basically, in free language, which means that phi of k will cause is the wrong word, but I think it's kind of, will cause phi of k. So that is how we actually use method of mathematical induction. This looks now a little bit more kind of abstract. My question is, will this abstract method connect with the story about the image? Can you recognize the connection? So basically, you see this fact that each domino will cause the next one to fall. So you say, all right, when I see that one domino is falling, and that's level k, then I need to prove that the next one will happen. And that's actually the main method of mathematical induction. And basically what? Principle sounds maybe somewhat abstract, but actually very useful. Why is that? Because you always use the information about your neighbor to make conclusion about your level. And you will see how helpful that might be. So let's see a couple of problems, actually. Some of you already saw that. So here is that statement. This is what phi of n is. So phi of n, someone says, oh, you know, I saw in the calculus book that the sum of first n squares equal to this expression. How did they get it? I have no idea. Of course, we can learn that in some other situations, looking at some recurrence relations. But let's say someone tells me that, and I want to check if it's true, because that's what proving is. So what can I do? So let me use the methodology. So I will say the following. I will start checking on different levels. You know, that's not part of the method, but I do it very often, like privately. I also check a first few members just for my own taste. So let me check n equals 1. Can someone help me to calculate when n equals 1, how much is this sum?
Would that just be 1?
Yes, because as soon as you say 1 squared, they cut you off because they said, cut it off when you say n squared. So if n is 1, as soon as I say 1 squared, I have nothing else. So I only have 1 square on the left. And then I put in question mark because I don't know if they are equal. On the right side, I have 1 times 2 times 3 over 6. And that's how much? That's 1. So what that person told me really works when n equals 1. And then what? Maybe this is, as I said, this is not part of the method. This is private kind of curiosity. Let me check it for n equals 2. As I said, just I'm a little bit suspicious. So what do I get here? On the left, I get 1 squared plus 2 squared. And I'm asking, is it true that that's equal to what? Can someone help me to calculate this? What do I get on top? 2 times what? 3 times 2n plus 1 is 5 over 6. And I cancel 6 and 6, and I get 5 equals 5. It's really good. But as I said, I can keep checking, but even if I check million members, I'm never sure if million first will not surprise me. So just, anecdotal evidence cannot prove this. So how can we use a method of mathematical induction to prove this? Generally, the fact that I can trust the formula at certain level might help me to conquer the next level. So that's how method goes. So let's recall. So we proved n equals 1, and that's done. And then we will assume that our theorem is true at certain level k. That's probably one of the trickiest levels. Which level is k? Any. So I'm talking general story, like about dominoes. You told me a minute ago, oh, each domino will hit the next one. What do you mean each domino? So kth domino will hit k plus 1. Is k 3 or 5 or 8? That work the same way because your argument is they are close. So whenever one of them falls, it will hit the next one. And that's exactly what we are proving. So we'll say, all right, we start with 1, and then we say, when I reach certain level, so the whole structure goes like this. I conquered the 1. Then can I reach the next one, which would be 2? And then 2 helps me to reach 3. 3 helps me to reach 4, like dominoes. And I will reach all the levels if I can show this inductive step. That's called a step. Wherever I am, I can go, I can progress for one more step. So what is that? Assume, so that's called inductive hypothesis. Assume we checked it for n equals k. Once again, how much is k? Doesn't matter. If it helps you psychologically, think that k is 43. So why, if I reach 43, how will that help me to conquer 44? That's the whole story. And generally, you want to do it in such a way that even number, if number is not specified, you can kind of produce the reasoning. So what does it mean that I assume we checked for n equals k? So that means for that k, left side looks like this. Right side looks like this. And I trust that this is true. I will put it in green color. That's usually people think that that's safe and good and stable. So generally, this is something that I can use. Very often when people do the proofs, they mix up what they can use as established and what they need to prove. So as I said, let's say secretly at 17, I know first of sum of the first 17 square is equal to 17, 18, I don't know, 35 over 6. Now I need to show that I can go an extra step, and that's tricky. So let me see. Usually I like to label those L of k plus 1. What is that? This left side, let me somehow color it. So this is my left side. I will plug in n to be k plus 1. So that's how left side looks like. So it says, add up the squares, 1 squared plus 2 squared plus, but don't stop at k squared, all the way to k plus 1 squared. So that is the expression I need somehow to summarize. And here comes the main skill in the induction. So this is the challenge level. So this is the blue level, let's say. So I have this to conquer to be equal to whatever. Oh, by the way, it's a good idea, but be careful what you do. What should I get on the right side to establish correctness? But don't write that here in the middle of the proof, because that might trick you so that you start using it. Let me put it here in this hidden spot outside of my calculation. How does the right side look like at that level k plus 1? What should I get at the end? This is like in my dreams. So what should I get? Can someone help me? 6 on the bottom. So that n that's here should be k plus 1. So it's k plus 1. Then what? Who's next?
K plus 2.
Mm-hmm. And then carefully, here when you plug k plus 1, you get 2 times k plus 1 plus 1. So that's not 2k plus 2. It is what? 2k plus
3.
3. Here it is. That's what I need to get at the end. And if I accomplish that, I'm done. So the main thing actually when you do the induction is connection between the neighbors. So if you know your neighbors, that's always to the benefit. Remember that. So let me see. My question is, how is green left and blue, is there a connection between them? Are they related somehow? That's the main skill in induction, and it's not always easy to see. Here it's fairly easy to see. What's happening? Oh, there are tons of chats. Sorry, I cannot follow it. Yes, yeah, see. Wait, for some reason, yeah. Okay, I see lots of comments. All right, so my question is, can you connect this green and this blue? Do they look quite similar, yes or no?
Yes.
What's the difference?
One is just slightly more than the other, which you can
Exactly.
kind of
They went the
multiply
same
it out.
way, just this one went an extra step. So among those dots, there is some k squared that's hidden there. And then what happens? And then I can definitely use and replace this according to my green assumption, because I know that that's the level that I conquered, that's the domino that fell. So I can just replace that, and that's my green trade. Maybe I should put it in green. So this is actually green part of the story, and I can replace it with k times k plus 1. That's 2k plus 1 over 6. And then blue guy's still there. I'm not done, unfortunately, but we made a big progress. Why are we so happy about our progress? Those dots are gone, no more dots. I just have 2 expressions. So I replaced 17 members. If k is 17, my hidden number, I express 17 expressions as only one. So now I need to deal with those 2 expressions. and get my number from my dream. Here it is. And generally, that is just basic algebra. Induction has nothing to do with it. So can someone help me to combine these two expressions to get a single fraction? What's a good idea? Big common denominator, standard business. So make it 6 here and multiply times 6 here. And then what? So as I said, just little polishing. So 6 on the bottom. And then I will add these two expressions on top. Good thing to save us from little writing. Do they have a common factor that I can pull out?
K plus 1.
K plus 1. So I pull that K plus 1 out. I will highlight it so that I know that that one is gone. So this is gone. And then who's left? Whoever's left, I will distribute. So that would be K times 2K is 2K squared plus K, and here 6K plus 6. Does this look promising? Let me go in my dream. So where is it? I lost it. Here it is. Good news is that K plus 1 is there. So my only hope is that this product here on top is equal to this expression here. So basically, and that is true because you can either factor it out or go backwards because that's really equal K plus 1 times K plus 2 times 2K plus 3 over 6, which is my right side. If you don't believe me, it's very easy. K times 2K is 2K squared. Here it is. Then 3K times 2 is 6K. Sorry, 3 times 2 is 6. And then K times 2 times 2K is 4K, and 3K is 7K, and that's exactly what I have. So that's it. So basically, a kind of using the connection between this blue level and the green level, I was able to replace majority of the member. And with a little algebra, I accomplished my formula at the next level. And that's the idea how induction goes. So use the information that you have on certain level to reach the next level. And what happens now? I've seen millions of proofs of using induction, and not only in textbook, in research papers here and there. So generally, induction is a really powerful method, but generally steps between K and K plus 1 are not always that easy. This one is quite straightforward. Actually, we teach this. This is a standard problem in our discrete mathematics course. And a few more of those standard induction problems. Next one will be about inequality. So here's an inequality that I would like to. So question is, when I had 1 plus 1 quarter plus 1 over 9 plus 1 over n squared, that always stays below 2. I was surprised. What if I take a million of them? Will it still stay below 2? What do you think? Okay, we'll go for a proof, but someone can say, how could someone think of this? I take millions and millions of members, and at the end, when I add them up, it stays below 2. Why is that? Arthur says 1 over infinity. Yes, generally what you want to say, there are lots of them, but they are getting small. Do you agree? Does this remind you of something that you saw in calculus? How many of you took Calc 2? Can you raise your hand, please? Okay, some of you. Okay, so I will just, for those that took calculus 2, I will just mention the argument that tells you that when you look at the series, sum of 1 over n squared, hyperharmonic series, when n goes 1 to infinity, according to the p-test, it converges. And generally, this is just partial sum of that one. So it definitely converges, no surprises. By the way, that sum is, I don't know, I don't think that they mentioned that in our course, is pi squared over 6. And that's not easy to prove, so that's interesting. So it might be a good honors paper in Calc. All right, so and pi squared over 6 is less than 2, so we are not surprised. But can you, without all that fancy calculus stuff, prove that this is less than 2? And I'll say, oh, I'm all fired up for induction. And this is a very neat problem. Actually tells you how sometimes things go wrong with induction. And this is a good example. And then we'll correct it, and it will work at the end. So if you are taking notes, you don't need to write this because I will fail on this one. So I'll use induction. So when n is 1, I just get 1 on the left, less than 2, and that's true. Then I will assume true for n equals k. So I'll go all the way to k, and it's k squared, and I'll go below 2. So that's okay, I can use that. And now I need to prove for n equals k. So I go 1 plus 1 quarter plus 1 over k squared plus 1 over k plus 1 squared is less than 2. And I'll say like a minute ago, oh, I'm happy because here is my green part. I know by my assumption that this guy is less than 2. Do you agree?
Yes.
But I'm stuck. Why? If this is less than 2, and if I add little tiny, can that get over the board? Yes, one
Yeah.
drop can make your glass spill over. So however tiny, if I'm below 2, maybe I would just about 2. When you add 1 over k plus 1 square, I'm not less than 2 anymore. So this didn't serve me well. Why? Because I don't know how close to 2 I am. Do I have enough space to fit that extra part? So this is where induction fails. And then someone thought of this, and in the homework, actually, we have this in discrete homework. Actually, the authors tell students that they say, but don't try it the way it's written. Try it a little different. And that is, prove that it's less than 2 minus 1 over n. Which is perfect. You are asking actually harder thing. Not only that I'm less than 2, but I'm less than 2 minus 1 over n. So you are taking a harder task. But why will this one be easier to prove? Because you have that little cushion, and then when that cushion can absorb that extra member, and you will see now I do it in no time. So what? Now assume true for n equals k. Now I don't need to go all the way to the 1 over n. I have 2 minus 1 over k. And then what? Then I just go easily. I said, all right, so this is less than, I get a little cushion. Because this is less than 2 minus 1 over k plus 1 over k plus 1 squared. So now I have a chance to have my cushion to absorb new member and get me on the right spot. What is the right spot in my dream? In my dream, it is the right side. It's 2 minus 1 over k plus 1. So I'm hoping that when I absorb this extra member, that I will make a little bigger denominator, but I will still be within the limits. And that's really true. So now it's just little algebra. So basically, it's interesting. I took a harder problem, but that one was easier to solve because, as I said, that cushion below 2 that gets changed actually gives me the chance to observe new members. So what do we do here? Just common denominator, 2 minus k times k plus 1 squared. And then what do I do? Can someone help me with this? K plus 1 squared minus k. I just did common denominator, which would be what? 2 minus. When you square this k plus 1 square, you will get k squared plus 2k. Now just basic algebra. So I'm just comparing the cushions. So what happens? I'll cancel this 1k and this k. Okay, and then I will say what? That this is less than or equal to minus. I will disregard this one. So I'll go k squared plus k over k times k plus 1 squared. In mathematics, you rarely see that someone says, oh, I'll disregard that. You know, my students would be very happy if they can disregard things and say, all right, I changed the problem, but it's fine. Is it okay that I disregarded this one? Because what? I subtracted the 2 expressions. So when I have 1, that expression is bigger. So here I'm subtracting more that I'm subtracting here. So when you're subtracting more, your result is less than when you're subtracting. So think about it. That's standard trick with inequalities. And then what do? We are done. Because when I factor out and cancel, exactly happens what I needed. K and k cancel, k plus 1 and k plus 1. And I get 2 minus 1 over k plus 1 from my limits. So you see, you rarely see that. Make it harder for yourself so that you have better connection between the levels. So that's a very interesting idea. All right. Any comments, any questions? Are we too serious on this or? All right. Let me do one interesting problem. Actually, it's less algebra. Both of those had some algebra or robust math. And next one is also something from number theory, but let me skip those. Or let me skip this. But let me talk about this one. How would you prove that any whole amount of money greater than or equal $8 can be paid using $3 bill and $5 bill? For example, I need to pay $74. Can I pay? Oh, don't challenge me on $3 bill. Problem was with 2 and 5, but I think 3 is nicer. So let's say there is a country somewhere, and they were imaginative with their banknotes. So they have $3 bill and $5 bill. Can you make $74 using $3 bill and $5 bill? I have no idea. Okay. So can we prove for all the amounts of money? I will use induction. But I will do some adjustments. So this will be a different induction than the one we saw previously. What is the starting value? Do we start from 1 here or we start from a different one? Because 1 cannot be done with $3 and $5, of course. So what is my starting value?
8.
8. So that's start of the induction. So of course, induction could be adjusted so that you don't start always from 1. Sometimes you start from 2, from 3. Things don't always start from the first value. So start n equals 8. Can you express 8 using 5 and $3? Yes or no? Yes, 5 plus 3. One of each. Makes sense? Now what? I will do the induction step. But my induction step will not be by 1, but I'll go for by 3. So induction step. If amount of k dollars could be presented using $3 and $5, then k plus $3 can also be present. I wanted this. First, is it easy to prove that? Assume that k is like 3a plus 5b. So let's say amount of k, and I know that k could be represented using a $3 bills and b $5 bills. What about k plus 3? What would that be? 3a plus 5b plus 3. Can this be done with $3 bill and $5 bill? Yes or no?
Yes.
Why? Because they're just an extra $3 bill. So it's 3 times a plus 1 plus 5. Was this easy? That was not a principle. I don't know if this will work. Because how will this do the job? I know domino 8 will fall. Do you agree? Using my principle, who will fall for sure? Would 11 fall?
Yes.
Yes, because that's extra 3. Who else? 14,
14.
17, 20. All those are done because of my principle, the inductive principle. But is everybody there who's missing there? What about 9 or 12? Or what about them? So, okay, 9 is missing. Can a 9 be presented using $3 and $5 bills? Yes or no?
Yes.
So besides 8, I also need to check 9, which is 3 times 3. But now when I have 9, who else do I get?
12
my
and 15
principle.
and 18.
12, 15, 18, 21, and so on. Is everybody here or someone still missing?
You also have to prove for the case of 10.
Yes. So 10, and 10 is okay. So I put it here. So n equals 10 is 2 times 5. So 10 is okay, and 10 will make 13, 16, 19, 22, and so on. What happens now? Did I cover everybody?
Yes.
Yes, because every number greater than or equal 8 either is in the same class as 8, which is the class of numbers of the form 3m plus 2. These are divisible by m, and these are 3m plus 1. So whatever number greater than or equal 8 you have, it will be covered by 1 plus 3. This makes sense. So what would be this principle? Can we formulate this principle so that we know when we decide to use it? So we can say induction with k plus, well, what's a good letter here? K plus s step. Or let me do k plus 3, the way we did it, and then of course it doesn't matter if it's 3. K plus 3 steps. So what do? Prove for the first three numbers on your list. And then what? Prove that phi of k implies phi of k plus 3. And then why? Because these first three numbers, each of them will cover its own group through this induction. So altogether, they will cover everybody. Is there anything special about this number 3? Could it be k plus 5 step? Yes, but then what? You need to prove the statement for first 5 values. So whatever your step is, that many values in the beginning should be proved, and then they cover everybody. So that's one adjustment of the induction. So sometimes you adjust the starting value, but you also adjust the step. All right. What else is there? So here is an interesting question. All right. Why don't I go here out of order? Imagine that someone asks you to prove this. That 1 plus 1 over n to the n is between 2 and 3, no matter how much is n. And what else? And that the sequence of those numbers is increasing. Any comment? Why would they ask you this question? That's what, often when I look at all the math problems in the journals here and there, I ask myself, how would they think about it? And usually things show up when you work on something and then something shows up and you have no idea, you start investigating and something comes up. But this is not one of those. This is a big one. Anyone recognizes what is this story all about? Why is this sequence important? This is the sequence that has, because that's exactly what you need to prove. This is the sequence that approaches one very important number. Actually, we know that limit when n goes to infinity of 1 plus 1 over n to the n is number e. And we know that's 2.7118 and so on. So basically, that's what it is, that sequence. But those that do calculus know that first it's a question, why when we keep changing n? First, the question is, why this is not exploding? Why does it stay below? Because it's bigger than 2, it's fairly easy. Because what? 1 plus 1 over 1 to the 1, that's 2. And then 1 plus 1 half to the square, what's that? 3 halves squared, this is 9 quarters. So this is a little bigger, and so on. And it's always bigger than 2, because when you do binomial formula, first 2 members will give you 2. Why is it less than or equal 3? If you are familiar with binomial formulas, that's not hard to show. But proving that this is an increasing sequence is quite tricky. What is it that you need to prove? You need to prove that 1 plus 1 over n to the n is less than 1 plus 1 over n plus 1 to the n plus 1. Why is that? Why is that important for a calculus course? Because when you know that that sequence is limited or bounded and monotone or increasing, then there is a theorem saying that those sequences must have a limit, and then it's legitimate to give it a name, and people gave it name E. So that's how you show, one way is to show that E exists. And what is E? So my question is, how do you prove this? And this is not user-friendly at all. Algebra, this is very unpleasant. And let me show you, when you do common denominator and all that business, you will get what? N plus 1 over n to the n is less than n plus 2 over n plus 1 to the n plus 1. So, what do you do there? You know, you don't have same base, you don't have the same denominators. And basically, let me give you a hint. I'm not gonna finish that, I'm not gonna ruin the fun for you. But basically, what people did is they said, all right, let me get that extra 1. So people did the following again, plus 1 to the n over. You don't do induction on this one because connection is very bad. So all right, so let me make at least exponent to be the same. N times extra n plus 2 over n plus 1. And then you get this guy on the left. So you get n plus 1 over n plus 2. Should be less than. When you cross multiply, you will get n squared plus 2n. Oh, I'm rushing this algebra because that's always the least interesting thing in the world. We need to do this. And again, doesn't sound promising at all. But basically, it is a one step to prove if you have this inequality. And this is the famous Bernoulli's inequality. So if you apply it carefully, you will get this in no time. My question is, why is Bernoulli's inequality? So it tells you that when you raise 1 plus h to a power n, you always get more than 1 plus nh, but be careful. N is a positive integer, but h is greater than or equal to negative. And basically proof is probably the easiest proof today. Such a powerful inequality, no time. And let me just illustrate how induction goes quickly. So I'll check it for n equals 1. So what does it say? 1 plus h to the 1 is greater than or equal to 1 plus h, which is true, of course. Now assume that 1 plus h to the k, so at certain level, the domino is falling. So on level k, let's say it is really true that left side beats the right side. So that's green, I can use that. And now we need to prove at level k plus 1. N equals k plus 1. So what would that be? And it's very easy. 1 plus h to the k plus 1. Why? Because connection between the levels is very easy. Because blue is the same as green with an extra copy. So I will repeat green times 1 plus h. And then green, according to inductive hypothesis, will be traded for green. So it will be greater than or equal 1 plus kh. And 1 plus h is just copy. And then if I FOIL, I easily get 1 plus kh plus h plus kh squared. And I get 1 plus, I'm rushing here, this is just basic algebra. Plus kh squared. I exactly got what I need. Plus extra. And that extra is non-negative because I have positive number in the square. So this is greater than or equal 1 plus k plus 1h. And that's it. So that's Bernoulli's inequality. Actually, there is one step that I did a little carelessly. And that is when I call the green inequality, which is here, I just copied 1 plus h. that's not always legal because it's inequality. So inequality, if you multiply inequality with a negative number, you flip it. So this is only legal if 1 plus h is non-negative. And is that true? That's why this condition is here, to make a legality of that move, that 1 plus h is greater or equal to 0. So basically, you can multiply both sides by 1 plus h, and you don't switch inequality. So here it is. It wasn't complicated. Connection between blue level and green level was very clear and simple. So that passage was done very nicely, and just minimum of technique was needed here. And as I said, if you want to play with this inequality here, actually you can just apply Bernoulli's inequality, carefully choosing h, and you get it in no time. Otherwise, you are in for a long trouble. All right, we promise to be done by this time. So what can we do? Generally, let me tell you a couple of other things I wanted to tell you, but obviously there's no time for that. But what are, I'll just comment on them. So sometimes induction is very nicely used for a divisibility argument. And for example, here is one interesting problem. Prove that 21 divides 4 to the n plus 1 plus 5 to the 2n minus 1. So it's not obvious at all why would such an expression be divisible by 21, but actually if you use induction, you can get it in no time. There is a little trick there. And basically, you know what I can definitely do besides the recording, I can just write neatly solution. I did write most of them, and then send you that one if you want to read on your own. So as I said, this is a good exercise where actually you test it when n is 1, and then try it from k to k plus 1. As I said, there is a little trick, and that should not be too complicated. Actually, when I talked to Ann Kelly about this talk, one of my plans was to show you something called the regressive induction, but we can do it some other time. Not all the talks could be done in just one meeting. So this is one of the most famous inequalities in mathematics. So if A1 up to AN are positive real numbers, then this expression, when you average them, it's called arithmetic mean. And this one is called geometric. And generally, arithmetic mean is always greater than or equal than arithmetic. And basically what? That proof is not simple at all. So in order to prove that, basically one nice proof for that is the proof where you use something called a regressive induction. And that regressive induction, just I'll put that and I'll finish. Regressive. You do the following. Number one, prove that it is true for infinitely many n's. Usually we choose a nice sequence increasing. So like we did in that case when we just proved every third member was kind of for one with the money. So prove that it's true for infinitely many numbers. And then what? Prove the following. Phi of n implies phi of n minus 1. So go backwards. Sometimes that's easier. And you can someone just tell me, why would that be valid? So basically, let's say I proved it 7, 33, 95, 152. So those are infinitely many, but I have big holes. What happens? Are you sure that it's true for 82? The answer is yes. Why? Because since I have infinitely many of them, I can always find some starting point that's above 82. And then I go backwards step by step using this induction, and I will hit 82. So you can say, why would I need that? For example, this proof greatly benefits from this technique. So generally, you don't go up, you go down, but you want to make it sure that you have enough starting points to actually get you down from some high number to the number that you. All right, and for fun, but this is quite tricky. This is such a combination of all types of induction. This is Erdős theorem, where actually you don't know even where to start. So, and it says if m is a positive integer, then among any 2m minus 1 integers, you can find m of them whose sum is divisible by m. So generally it says if m is, let's say, 10. So if I have 19 numbers, I can find 10 of them. When I add them up, it's divisible by 10. Not clear at all where is this coming from, but actually it is true, and it's very interesting. So generally, if you are interested in any of these, just stop by my office, send me an email. Keep reading, keep investigating in that direction, and I hope you will enjoy induction in your studies and in your. That was my talk.